My name is Jason Wagner. I'm an associate transportation researcher with TTI. And I've been researching automated and connected vehicles for about the last 4 years and some of the implications and effects that they might have on transportation agencies and the transportation system in general. As a caveat real quick, I am not an engineer. It's not my background, but I did do a bit of brainstorming with some engineers at TTI and did a little bit of research into the specific area. So hopefully we'll have an informative and at least thought-provoking discussion today about some of the issues. So to give you a quick overview of the topic, we're going to start off with describing the two technologies of interest, looking at automated versus connected vehicles. We're going to try to understand the differences between the two, what are some of the benefits, the way they work. We're going to dig into definitions between the differences between the different terms and the terminology. There's a lot of things that are thrown out there: fully automated, self-driving, autonomous, automated, all these things. What do these different things mean, and what are the correct terms to be using? Then we're going to dig into getting under the hood. How do automated and connected vehicles really work? What are the systems that enable them? What are some of their capabilities and limitations? Shifting from this, we're going to start looking at the implications for design and infrastructure. There's quite a bit of uncertainty. We're going to go through some of the things that we don't know. From there, we're going to look at what do we actually know. And based on that, what do we do with that information, and when should we make any decisions, or when should we start acting based on that? So, autonomous, automated, self-driving, fully automated, et cetera, et cetera. There's a lot of different terms, and the media does a pretty good job of using all of them pretty much interchangeably. So it makes it a little hard to really figure out what we're talking about specifically. There's a distinction that might be important for our talk today: autonomous versus automated. And one of these terms is a little bit better. Autonomous, when you look at the definition, it really means that something is existing or acting in and of itself. It's really a self-contained system, and it's not gathering information or gathering resources from outside of itself. Automated, by contrast, is a term that essentially means to take a process that was previously performed by humans and to simply automate it, or let a machine do the work instead. And as we're going to see, that's an important distinction because a lot of the vehicles of tomorrow are really likely to rely on connectivity and information from the outside sources. So they're really not just going to be autonomous, they're going to be drawing on lots of information from the environment. So how do automated vehicles work? Well, they gather and integrate information from a variety of sensors that are placed on the vehicle to help them understand the world. Based on that information, there are electronic control systems on board that actually take charge of the driving, the steering, the accelerating, the braking, etc. Going through these really quickly, radar is a long-standing sensor. It's been developed around World War I, and it's been in use for quite a while. Essentially, it sends out a radio or a microwave from an original point, bounces off an object, returns to the original vehicle, and based on that information, you can determine what or where the object is, how quickly it's moving, that sort of stuff. LiDAR is a portmanteau, actually, of the words light and radar. If you just jam them together, you get LiDAR. And this system is essentially it's a spinning disc. Well, let me see. You can see up there, that's basically a LiDAR. And it's on top of a lot of different test vehicles of today. It's a pretty expensive technology, and it's probably not going to be commercially available for commercial use for quite some time due to its expense. Cameras and GPS, both pretty traditional technologies or well-developed technologies. A lot of automated vehicles of today rely on digital camera systems. Ultrasonic sensors, these are basically sonars. If you can see the little purple area immediately direct to the vehicle, it's basically a short distance sensor that can only detect what's right in close proximity to the vehicle. It uses sound to determine that. And finally, HD maps. And what you see here, the baseline, this is first off the Google car. This is an example from their software system. And this is the way it sees and interprets the world. This baseline here is an HD map, a high definition map. And what they have is a fleet of vehicles that are equipped with LiDARs that go out and map the environment so that they have a baseline expectation of knowledge so that when their vehicles go out, they can use their additional sensors to help them triangulate and navigate through the world. As you can see here, this is the LiDAR in the front of the grille. That is a radar and a digital camera. This picture down here illustrates what the vehicle is actually seeing. And these little shapes on the side of the road are essentially representations of objects that the vehicle wants to avoid and that it's detected from its internal sensors. So it's got the baseline HD map that it has, and then it uses all of its other sensors to really figure out where it is in the world and uses all this information fuses it in order to navigate the environment. So, how do we classify automated vehicles? How do we talk about these systems? There is a current standard from the SAE, the Society of Automotive Engineers International. It's J3016, and it ranges from level 0 through 5. The lower level vehicles, 0, 1, and 2, the human is primarily responsible for the driving task. There are limited systems called ADAS, or Advanced Driver Assistance Systems, that essentially just help out the driver. Things like adaptive braking, adaptive cruise control, forward collision warning. All these systems are essentially just minor automation that's just designed to make driving safer, a little bit easier. Once you get into the higher levels of automation, this is where the vehicle is really taking over the primary control, and the human is no longer necessarily responsible for monitoring the driving environment in all situations. Breaking this out into the full chart, you can see, so this is about where today's on-road vehicles are. The most advanced vehicles are about level 2, and the current testing vehicles are around level 3 to 4. And basically what this means is the higher level vehicles are capable of driving in most, but not necessarily all situations. They may need to sometimes revert to a driver who's in the vehicle. That's why Uber and a lot of the other test vehicle companies have drivers that ride along. If it experiences something that it can't necessarily handle, it'll defer back to the driver who will take over. Let's see, moving on. So now we've got a baseline of understanding about automated vehicles. What about connected vehicles? This is a little bit of a different system, and people are usually a little less familiar with it. Connected vehicle essentially means, or is a system that the US DOT, the US federal government, has been developing over the last 10 to 15 years. And essentially it enables vehicles to talk to each other, to communicate with each other, the infrastructure and other modes of transportation through 5.9 gigahertz of DSRC. That stands for Dedicated Short-Range Communication. It's kind of like a radio in a car that basically sends messages at a short range to other vehicles, to the infrastructure. There's a phrase for the message that it's called the basic safety message. It's also called the "Here I Am" message, because it is essentially the vehicle broadcasting to the world, "Here I am and here's where I'm going." You can use this information to develop a variety of traffic applications that enable you to route traffic or give drivers warnings and information that can increase the transportation system effectiveness and efficiency and safety. These are known as V2V, vehicle to vehicle, V2I, vehicle to infrastructure, or V2X, which is basically vehicle to some other mode of transportation like pedestrians, cyclists, motorcyclists. The focus of many of the applications, the earliest applications have been on safety, but there are also environmental and mobility applications as well. And to emphasize, this is not a telematics system that we're most familiar with. This isn't OnStar, this isn't Verizon, this isn't AT&T, it's none of those things. It's a US DOT program that's totally separate from all that. So why is connected vehicle important? Well, there is a nice saying that anything you can do unconnected, you can do better connected. Basically, today's automated vehicles, and likely tomorrow's automated vehicles, will function similarly to what a human does, in that we use our own senses, vision or hearing, to really help us understand what's going on in the world. Automated vehicles also use onboard sensors to help them understand, so they're really limited from their own perspective to the information that they can gather. What they can gather from their LiDAR, from their radar, from these different sensors that are on board. So it's really limited to a relatively line of sight type distance. With connected vehicle, you can get a much more rich set of information, and you can, with using this information, you can have much better control of your vehicle, because you will know potentially what's coming up ahead, and you can prevent collisions, you can reduce congestion, and you can provide a lot of environmental benefits, all through this additional information set. This is a truncated set of some of the applications that the federal government has developed for connected vehicle systems. As you can see, there's V2I safety, it's vehicle to infrastructure, V2V, or vehicle to vehicle safety, road weather, environment, some agency data applications that can improve the way agencies handle their information and gives them more information about their operations on the road, mobility applications, as well as some smart roadside. And this is, like I said, a truncated list. It's actually a longer one, but it wouldn't fit nicely on the slide, so I cut it down a little bit. So, based on what we know about automated and connected vehicles, what are some conclusions or some implications that we can draw about design and infrastructure? Well, to start off, there is a huge amount of uncertainty. These vehicles are not yet fully developed. They're really in the testing phase. They're out on the roads and streets, but they're not really sharing a ton of data. So there's a huge amount of things that we don't know. We don't know how humans are going to adopt them and use them, and we don't know what the effects on the transportation system might be. So, for example, VMT and congestion. When people start using an automated vehicle, we know it's likely to decrease their cost of transportation because they're no longer the ones who are actively engaged in the cost of driving. They're the ones that can spend their time doing other things. You can use your time more effectively and more efficiently. So if people are a little less, if they dislike the act of driving a little less, maybe they'll drive a little more. But there's also some pretty good arguments that you can make for why VMT might decrease in some situations. So there's really a lot of uncertainty in this regard. Deployment timeline, there's a lot of people saying maybe as soon as 2020 we'll have highly automated vehicles, maybe 2030 up to 2050. There's a wide amount of variation, although in recent years there's been a lot more optimism in terms of the time frame being a little bit closer rather than farther away. There's questions about the capabilities and limitations of automated and connected vehicles. How will they be able to handle poor weather? How will they be able to handle, will they be way more safe than human drivers? Will they be able to handle driving in a much smaller lane? Will their controls be much more precise? All these are questions that we don't yet completely know. And if it is going to be better, how much better? What is the percent increase in these different factors? These are all important, especially when you're talking about things like design. What about vehicle design? If you go back and look at especially some of the pictures of the older vehicles, like we saw in the earlier talk, some of those older vehicles, like the Model T, our vehicles today look nothing like that. So how do we expect that vehicle design is going to change as a result of automation? Will it change? It seems likely that given the different capabilities and different features of automated vehicles, that consumers might want different things out of their vehicles, and the average vehicle size or shape might change. Will that have some potential implications on design? It's a good question. Does ownership model make a difference? So automated vehicles are pretty expensive due to all their onboard sensors, and when they're initially deployed, the most logical economic model is going to be distributing those costs across a large number of consumers. If a vehicle costs $300,000, your average consumer is not going to be able to purchase that vehicle. But a fleet of Ubers or a fleet of other self-driving vehicles might or would be able to recoup their costs, and some economic projections have shown that they would likely be less expensive than a current vehicle to own and operate on a per mile basis. So there's definitely some economics that are in favor of a shared vehicle or a shared ownership model, at least in the early days. Will that have any implications for these other factors? There's certainly some possibilities there. Finally, human adoption and adaptation. When humans have adopted new transportation technologies throughout human history, they've tended to really drastically change the way humans live in their environment. You can think of all the way back to the Native Americans, the introduction of horses. They were much more mobile. They were able to move about and actually have more wars and be much more mobile through their environment. The transcontinental railroad, the automobile, all of these things drastically changed the way people lived in their environment and the way they moved through it. And as a result, people changed their behaviors as well. So will automated vehicles, which are most likely going to have some pretty drastic differences from our current mode of transportation, will they invoke some similar changes? These are all things that we don't know. So, we don't know a lot. What do we know? Well, we do know that today's limitations are probably not going to be the same for tomorrow's systems, and it might be a bad idea to plan or design our systems based on today's limitations. The earliest vehicles, like the Model T, were a lot less capable than, say, today's Land Rover. There's a big difference in those two. And so if you're designing a road for a Model T versus a Land Rover of today, you probably would be designing roads a little bit differently. So it might be a mistake to take, for example, the limitation of digital cameras. So right now, if you have a vehicle with adaptive cruise control or some sort of system like this, it's probably using digital cameras as the primary method of observing the road and gathering information. These systems work relatively well, but they are also heavily reliant on lane lines. And without lane lines, they tend to have trouble, especially doing things like lane keeping. It's hard to know where you are in a lane if there's no lane lines to keep you in there. But this may not always be the case. Things may change in the future, and things are likely to change, so it may not be the best idea to set standards according to this. GPS accuracy is another example. It's got about 3 meters of accuracy. It's about 10 feet. It's nowhere near as good as OEMs and automobile manufacturers would like it, but that's not necessarily always going to be the limitation. Several sensors, like LiDAR, are heavily affected by weather. They can't function in snow or heavy rain, fog, these sorts of things. So that's a limitation. But is it always going to be that way? Probably not. We also know that automated and connected vehicles are not human. Seems like a pretty obvious thing, but it's relevant and important for this discussion. So we know that some design principles of today rely and assume that there's going to be a human operator in the mix. For example, there's a sight distance and perception reaction times model. A lot of speed limits are set based on the assumption that the human is going to be in the driver's seat and they will be the ones having to stop. And so for this, we're going to dig a little bit to the stopping sight distance model. So this particular model is a function of the distance traveled during human perception and reaction plus the braking distance. So if you break that down, a human, when they see a brake light to a vehicle in front of them, the light has to travel from the brake lights into their eye, and it has to, that information has to travel from your eye all the way into your brain. Your brain has to process and recognize that yes, that vehicle is stopping, and then it has to figure out what do I do based on that information. Once it's figured out what the appropriate action is, it has to tell your foot, all right, actually press down the brakes. All of that time period is a certain amount of time. And that's basically built into some design principles. If you replace this time period with a superhuman and very fast computer, which is able to execute this in a much quicker fashion, the underlying assumptions may no longer hold valid. And we may need to revisit them once these technologies continue to evolve and develop. So that's a little bit related to automated vehicles. What about connected vehicles? Well, as I was saying earlier, connectivity, anything you can do unconnected, you can do better connected. And connectivity can really enable some system-level benefits, enabling, in this example, for example, like vehicles being able to see around corners. To blow this up a little bit bigger, as you can see here, this is, by the way, from the US Department of Transportation. They gave a series of webinars related to connected vehicles and applications that might be used, and this is one such example. In this example, there's a major interstate intersecting with a rural, maybe a farm-to-market road. And as you can see, there's a little bit of vegetation here on the side of the road that might be causing a problem for the driver who's trying to cross it. He may not see that oncoming bus, and without any connectivity, he might potentially get hit by the bus because he assumes that there's no vehicles that are coming. However, with the use of connectivity, you've got, for example, here's a roadside sensor. There's a roadside sensor here and a roadside sensor here that are collecting data from the vehicles in the environment, and then it is processing that data and sending it out to the other vehicles in the area. And based on that information, knowing where the vehicles are and knowing where they're heading, you can let vehicles at the minor road know that it is safe or not safe to cross. So in this way, your vehicle is no longer limited by just your physical ability to see, or your vehicle's ability to see using its LiDAR, radar, these types of systems. According to the US DOT, they projected that the impacts could be, of this specific application, significant reductions in collisions, injuries, and fatalities, and that non-recurring congestion as a result of collisions could reduce as much as 30%. So, based on all this information, what do we do? What is the proper course of action? Do we change the infrastructure design to leverage new capabilities of these automated and connected vehicles? Do we, for example, change speed limits? Out in West Texas, it's pretty easy to drive a long way on a pretty flat and straight road, but humans may not have always the best reaction time, and they get a little tired and might get a little drowsy, maybe veer off the road. Automated vehicles are probably not going to be getting tired when they're driving across a boring stretch of West Texas. So you might be able to change the speed limits potentially, put them a little higher. Knowing that you have additional connectivity from additional information. You know what's further down the road than what you can just see with your sight lines or with your ability to see or your vehicle's onboard sensors. So you might actually have increased reaction times and just a safer environment in general. Advisory signs and warnings, like if you have to slow down to take a curve, for example, automated vehicles may be able to navigate these situations a little more precisely or a little better than humans can today. So maybe we can change some of these or revisit their needs. Like we saw earlier, there's some potential changes related to intersection design. And one thing that's come up quite a bit is the possibility that there could be narrower lanes. So if automated vehicles are much more precise in their handling capabilities, maybe we change our lane design and shrink it a little bit to potentially fit more lanes on a given roadway. And then, of course, there's also the option or the possibility of changing actual operations. Excuse me. I've got a video here that shows essentially that. This is from MIT. And what they did here is they show, well, here we'll start off with a traditional intersection design. And what they developed was a slot-based algorithm that automatically routes traffic. The vehicles slow down as they're approaching the intersection because they know what vehicles are coming from the other direction, and the intersection is essentially directing those vehicles when the best time is to move through. So they adjust their speed as they're approaching in order to allow the vehicles to free flow and route directly. As you can see, there's a decrease in pollution according or against the traditional design. Again, that was from MIT. So, when do we make changes? We know that there's some things that we might be able to do, but when do we make these changes? So, again, the huge amount of uncertainty. I can't emphasize this enough. There's a lot that we don't know, and so that's really going to influence what we can do and how precise we can make these predictions. But we can say that for sure, in the near to medium term, at least the next 10 years, at least, there's going to be for sure a mixed fleet, but still with humans in the mix. It takes about 12 years for the vehicle fleet to turn over, so even if highly automated vehicles came into being tomorrow and were mandated, it would still take probably at least 12 years for most of the fleet to turn over. So again, it's okay to assume, at least in the next 10 years, that there's still going to be a mixed fleet, so we probably should continue to assume that humans are the kind of weakest link in this chain, and we should still design around them. But longer term, there's definitely some opportunities to change design and increase efficiency, safety, to take advantage of these vehicles and their new technologies and their new capabilities. So with that, thank you very much. I'm Jason Wagner. If you have any questions, this is how you can reach me. We do have a few minutes left for question and answers, by the way. If you got it. Great question. Yeah, the question was, what about animals in the road? So there's actually a really funny anecdote from Google. They put out some stuff every once in a while, according to at least California has some regulations that they have to put out information about crash reports, etc. And they had an interesting video from their LiDAR where there is a goose in the middle of the road and a woman in a wheelchair chasing the goose around and around and around and around in circles in the middle of the road. And the Google vehicle did probably what you or I would do. It pulled up and it observed the situation and it just stopped. It sat there and it watched and it waited. And they kept going for about 30 seconds, and then eventually they moved out of the road and kept going, and the Google car kept going as well. So similar to the way people adapt to new information, when strange things happen and we don't know what to do, we kind of just sit there and wait and, well, wait until it's safe to continue, and then they continue on their way as well. So yeah, probably not a huge barrier. Anybody else? In the middle. Sure. Sorry. Mandate, good question, by the way. The question was, who is the mandate, or what mandate was I referring to, and when might this occur, who would be doing it? So this was a mandate related to connected vehicle more than automated vehicle. And the connected vehicle system is dependent upon the DSRC, the Dedicated Short Range Communication Receiver in a vehicle. And NHTSA will be mandating this. They've announced their advanced notice of proposed rulemaking. They've advanced their notice of proposed rulemaking. And the expectation is that the rule will actually be made probably somewhere in the next year or two, and that the mandate will take place somewhere around 2020 for the connected vehicle system. There's no such mandate related to automated vehicles at all. Anybody else? On the right? Reduce VMT. Yeah, that's a good question. Let me think about that real quick. There have been some people suggesting that if you're changing the way that people interact with their vehicles, like if they're shared vehicles, for example, you might take fewer trips, you might consolidate, you might travel less I guess in general, it's a harder case to make, but I've heard people make it. Maybe that people would travel, take fewer trips, yeah, that sort of a thing. Back left.
The computer system wasn't working properly. What would happen in that?
Yeah, sure. So the question is, what if the computer system stops working? So if we go back, wow, basically the system has to be designed in such a way that it's able to handle errors like that. The Google system has some sort of a fallback mode. So their earlier vehicles had like a steering wheel in the car and like a big red button that you could press that if everything went wrong, you could just press that and it would return to human driving. And certainly some of the earlier systems have capability that if something's going on, you can just pull the wheel or hit the brake and you'll take over instead. Some of the other vehicles where there's not even a steering wheel or brake pedals, the system has to essentially be fail-safe. It has to be able to work in all situations because obviously there's no opportunity for a driver to take over. And there may be some sort of a fallback mode programmed where it pulls over to the side of the road. And that's a great question. There's some variation based on how that would occur. I've heard different things from different manufacturers. Some manufacturers, I think Mercedes has a plan where they have like an actual in-car system that's like monitoring the driver. So if something happens to the driver while their automated vehicle is driving, like say you have a heart attack while your automated vehicle is driving and you're incapacitated, the vehicle knows to pull over to the side of the road and just stop because their current vehicles are not able to handle all situations in self-driving mode. So they had to have some sort of a fallback mode built into place. In the middle? Sorry. Oh, down here, down front. Sorry, I missed you. Yeah.
I've seen changes in the design standards that will have to be looked at here like that, but what skill set, tools do the design engineers need to have to get ready for this? And particularly when you're talking about the HD maps that these cars have to use, when a road is under construction, how do you get the details to the updates of the mapping while it's under different phases of construction?
Okay, so the question was, how do you get, I'm sorry, so it's how do you get the information, say if you have a construction work zone going on, how do you notify the vehicles that there's a work zone and that they need to be able to handle that situation, that sort of thing?
You said that it had to do with HD maps.
Yes, sir.
I assume those are when the road is normal. But
Yep.
when you go under construction, and also you have these different lane configurations, movements, and things like that, that's no longer matches the base model.
Yeah, sure. So again, if there is a change in the infrastructure, especially for construction, and your system is dependent on HD maps, which presumably were maps before the change, how would your system handle that? Good question. So there's variations between different manufacturers. Some manufacturers say that they don't even need HD maps, that's something that they don't want to have to rely on. So that's, again, it's still very early days, and so there's a lot of different systems that different companies are using. So that's not necessarily always going to be a prerequisite. That being said, the current systems that I've seen demonstrated are usually capable of handling work zones. Like if we go back, there's actually, where am I? This one. Yeah, that way. In the Google vehicle model, all the way at the beginning. So they're actually in a work zone right here. So you can see that the camera has actually noticed that there are cones here. And they've plotted the route, and this is all being done basically in real time. They've figured out that means they need to go around, and they've shifted over their course to go around the lane, or the cones, and to continue on their way. A lot of the systems some systems have been developing machine learning through image recognition. So basically, they can look at the environment and they can identify that that's a cone, or that there is a person waving a flag, or holding a stop sign, or all these sorts of things, and that they understand the context and what those signs mean, and that they are essentially adaptive enough, somewhat like humans, to figure out what to do in those sorts of situations. I've seen some, even like NVIDIA recently came out with their own, relatively very recently, vehicle, and they demonstrated it in work zone in a situation exactly like that, where their system is definitely not the most well developed, but it was able to handle some novel arrangements where there were traffic cones or different configurations where the road was being worked on, going on like a gravel road around it. So I think the vehicles, especially when they come to market, are going to be able to handle pretty much any situation that you're going to throw at them. And if they don't, then it's going to be probably a pretty big liability on the manufacturers, because if you put humans in the car, the vehicle has to be able to perform safely. So, we got one more in the middle. Yeah, so the question was, there's never been a safe that someone's not been able to crack. There's never been an IT system that's been completely foolproof. How do we know that our vehicles are going to be foolproof? That's a great question. A lot of the systems that are being developed to control vehicles are separate from like infotainment systems. That's one barrier that they've built in. So like if you have less secure systems, they're not at all related to, or they don't connect at all with the onboard electronics and the control systems. They're totally separate systems. But that's a great question, and I think it's going to be something that we're going to have to wait and see, to be quite honest.